So inverse matrices and systems. So to lead up to what we're going to do with matrices, and we kind of talked about it a little bit. If we had an easy algebra equation, so if we had AX equals B, and A and B are just real numbers, what would we do to solve for X here? Divide by A, right? And we can think of dividing by A as being the same thing as multiplying by 1 over A. So I'm going to multiply both sides by 1 over A. So we get X equals 1 over A times B. And dividing by A is the inverse operation of multiplying by A. So we're going to do the same thing with matrices. And A times 1 over A gives us just 1, right? So with matrices, if we had the matrix equation, AX equals B, we're going to follow the same, we want to solve this the same way. We're going to multiply by the inverse of the matrix. We don't really have a procedure for dividing by matrices, so we're going to multiply by the inverse. So same thing we're doing here, we're kind of doing the inverse operation. We're doing the inverse operation here. And just like A divided by A is 1, A inverse times A gives us the identity matrix. We said the identity matrix X like the number 1 for matrices. And the identity matrix times the matrix, what does that do to the matrix? What did our identity transformation do to our point the other day? Left it the same. It didn't do anything, right? So this just gives me X, this matrix X equals A inverse times B. So that's what we're going to do to solve a system of equations using inverse matrices. So we need to do a couple of things before we actually get to the procedure. First, we need to know how do we know what is an inverse matrix, and we need to know how to find it. So an inverse matrix. Our matrices have to be squared. So if our matrix isn't square, we can't find an inverse. And square means our dimensions, our order is n by n. And the way that an inverse matrix works is A inverse times the matrix itself equals, and it doesn't matter which order I multiply these two in, gives us the identity matrix. So if I multiply them in either order, I get the identity matrix. So that's how we know when we have an identity matrix. We can multiply it by the original matrix and see if we get the identity. So some of your homework problems will say, for example, show that B is the inverse of A. And we're going to say B is the matrix (1, -6, 1, -5), and A is the matrix (-5, 6, -1, 1). So there are two matrices. To show that these are inverses of each other, what the problem is asking us to do is multiply them together. A times B and B times A, and see if we get the identity matrix. So let's do the multiplication. 1, -6, 1, -5, times -5, 6, -1, 1. So we're going to multiply this out. So first row, first column, I get -5 plus 6, get 1. First row, second column, I get 6 minus 6, 0. Second row, first column, -5 plus 5, 0. Second row, second column, I get 6 minus 5. So I get the identity matrix. And then I need to show that it works in the other order as well. So -5, 6, -1, 1. So we multiply in the opposite order. And in first row, first column, I get -5 plus 6. You get 1. First row, second column, I get -30 plus 30. You get 0. Second row, first column, -1 plus 1, 0. Second row, second column, 6 minus 5, 1. That shows that these two matrices are inverses of each other. If either one of them doesn't end up with the identity matrix, then they would not be inverses of each other. So that's how we figure out if one matrix is the inverse of the other. So we're good with that idea. Okay. Not all matrices have inverses. So sometimes we won't be able to find an inverse. If a square matrix doesn't have an inverse, it's called singular. And in a little bit we'll do a couple of things with our calculator. And if we have a matrix, if we try to use a matrix and we try to find the inverse with our calculator, your calculator will say error singular matrix. And what that means is it doesn't have an inverse. And when we go to solve problems with a singular matrix, that means we have to do a little more work. So now we need to know, how do we find an inverse matrix? So in numbers, it's easy to find the inverse. We divide, we subtract, we know the inverse operation. With matrices, it's a little more involved, but we're lucky because some nice things happen. So for a 2 by 2, for example, let's say we had a matrix A, and this is just the matrix A, B, C, D. And we know A, B, C, and D. We have some numbers. And we want to find the inverse. We don't know the numbers that go in this matrix. So I'm going to call them X, Y, Z, and T. But what we do know is that A times A inverse is the identity matrix. If I multiply these two out, I know A, B, C, and D. If I multiply these two out, I get 4 equations, one for each of these numbers in the matrix, and 4 variables. So in order to find the inverse of this 2 by 2 matrix, you solve 4 equations with 4 variables. That doesn't sound like much fun. It's not much fun. But luckily what we do in math is, what mathematicians do is look for patterns and try to figure out shortcuts. So for a 2 by 2 matrix, mathematicians did this process, solving these four equations, four variables, and they said, hey, it looks like something's going on here. There's a pattern here. So they find this pattern. For a 2 by 2 matrix, the pattern is really easy. Instead of doing, after doing this a whole bunch of times, found this pattern. If we have A is this matrix A, B, C, D, the pattern that mathematicians found was that the inverse is 1 over the determinant of A times the matrix I get when I switch these two and change the sign on these two. And that's all I have to do to find the inverse of a 2 by 2. For a 3 by 3, the process is a little more involved. So for a 3 by 3, we will use our calculators. But for a 2 by 2, find the determinant, which we know how to do now, and I switch the two elements on the main diagonal, switch the signs on the two on the other diagonal. Yeah?
So how does it know it's right?
The determinant, good question. Let me get to that in just a second. This matrix, if you go further, if you study linear algebra, this matrix that you get by doing this process comes up relatively frequently. It's called the adjoint or adjugate matrix. So the process you go about to do this, the process with a 3 by 3 or 4 by 4, a little more involved, but we call that the adjoint or the adjugate matrix, and that comes up in other applications. To answer Declan's question, how do we know if it doesn't work? If the determinant is 0, so if we do this determinant, if it's 0, the matrix does not have an inverse. So that's how we can tell whether or not we can find an inverse. If the determinant is 0, our matrix does not have an inverse. So a fairly easy test. Then we have a singular matrix, and then if we're solving a problem with that, we have to do a little more work. All right, so let's. I want to do one example of finding the inverse of a matrix, of a 2 by 2 matrix. Then we'll see how we use that to solve a system of equations. All right, so questions on this process. Okay, so if we want to find the inverse of the matrix 4, 5, let's say A equals 4, 5, 7, 9. Do I want to do that one? Is that the one I want to do? I want to do one with different numbers. Sorry. Just a little easier to calculate with this one. 3295. All right, so the first thing we need to do is find the determinant. The determinant of A is 15 minus 18. So we get -3. So the inverse is -1/3, 1 over the determinant, times the matrix we get when we switch the 2 on the main diagonal, change the sign on these other 2. There's my inverse matrix. And you can leave it written just like that, that's fine. That's all we have to do to find the inverse of a 2 by 2. And we could verify by multiplying these two together, and we'd see that we get the identity matrix. All right, so questions on the process? So what we're going to do with this, and we kind of at the beginning of the talk today we mentioned it, and we talked about it a little bit before. Yeah. No, so if I multiplied this in, I would just get negative 5/3, 2/3, positive 2/3. Is that what you asked?
Yeah.
Then I would get 3, negative 1. But if I multiplied this matrix times this, I would get the identity matrix. And the easy way to do that would be to multiply these two and then divide everything by negative 3. And you'd get the identity matrix. A times A inverse would give you the identity. So the way we're going to use this is if we have a system of equations. 2x minus 5y equals 8. 3x minus 8y equals 1. So there's our system of equations. We're going to rewrite this as a matrix equation. So I'm going to write 2, negative 5, 3, negative 8, times the column matrix xy equals the column matrix 8, 1. And if I multiply this out, I'd get 2x minus 5y equals 8, and 3x minus 8y equals 1. So I rewrite this as a matrix equation. I'm going to call this A, matrix A, call this big matrix X and B. And to solve this, we're going to say X equals A inverse times B. So we're just going to multiply the inverse of A times this column matrix. We know how to find the inverse. We can multiply it by this column matrix. Now, before we do that, the interesting thing about what we do is a 2 by 2 system relatively easy to solve by hand. So we're doing the easiest thing to do. The reason we're doing this is so you see the process. Computers are really good at working with matrices. So you can program computers to solve systems of equations by matrices. But in order to program the computer how to do this, you need to know what it's doing. So that's part of the reason we're doing this. We want to understand the process, so that we want to kind of mechanize it with a computer. It's easy to do that with the computer does as well, but we need to know what's going on. We need to know how to tell the computer how to do that. All right, so let's solve this problem. So to find A inverse, the determinant, if we call this matrix A, the determinant of matrix A is negative 16 plus 15, so we get negative 1. So A inverse is this matrix. Negative 1 over 1 is just negative 1, times the matrix. I'm going to switch the elements on the main diagonal. Change the signs on the other two. So I get the matrix 8, negative 5, 3, negative 2. So there's my inverse, and I would get that X, the big column matrix, X equals the matrix 8, negative 5, 3, negative 2. times the matrix 8, 1. And if I multiply that out, I would see that x equals, not going to do the multiplication. Hopefully we can see how to do that. We get this matrix, and that would tell us that x equals 59 and y equals 22. That would be the solution to this system of equations.
How do you know what order when they multiply b first or
You, in order for the multiplication to work, you have to multiply on the left, because since a inverse is 2 by 2, if you multiplied it on the other side, the multiplication wouldn't work. So this is 2 by 1. We couldn't multiply a 2 by 1 by 2 by 2. You have to do it the other way. So you're always multiplying on the left in order for the multiplication to work out correctly. All right, questions on that process? So this is how we use matrices to solve systems of equations. We find our inverse matrix and multiply our matrix of constants by the inverse matrix, and that gives us our solutions. All right, so I want to do one where the determinant of our matrix doesn't come out to be positive or negative 1. So that I want to show you what we do in that case. Just a little time saver. All right, so let's look at another example. This one, we'll just say we have this matrix. We've already written it as a matrix equation. So there's our matrix equation. And I just made this equation up off the top of my head. Oh, is this going to work? I'm going to do 8 to make sure when I looked at that, I thought that the determinant might be 0. So I want to make sure the determinant's not 0. All right, so I'm going to call this matrix A, that capital matrix X, and that B, and we know that X is A inverse times B. We need to find the inverse of A. So the first thing we do is find the determinant. And for this one, the determinant is negative 8 minus 6. So negative 8 minus 6 is negative 12. Is that right? Negative 14. So A inverse is minus 1/14, or 1/14, minus 1/14. We're going to switch the elements on the main diagonal, change the sign on the other two. So there's my inverse. And we know that X equals this inverse matrix Did I forget to switch a sign? This should be a negative 2. Times negative 3 pi. When we get a problem like this, where our determinant isn't 1, where we end up with a fraction for our 1 over our determinant, multiply these two matrices together and then divide by the negative 14. So instead of dealing with the fractions. So if we continued with this one, I would just leave this negative 1/14 out here and multiply these two together. So we get, for the first row, multiplying the row times the column, we get negative 24 minus 15. So we get negative 39. And for the second row and the column, we get 6 minus 5, so 1. And then we can multiply through by the negative 14, so negative 1/14, so we get 39 14ths and negative 1 14th for our solution. So multiply through by that fraction right at the end. Because otherwise you're going to be dealing with fractions all the way through that calculation. And this is a little easier than you'd end up dealing with when you solve this system of equations. You'd end up dealing with these fractions a little easier than dealing with all those fractions. All right, questions on our process here. Okay, let's take a look at how we're going to use our calculator if we have a larger system of equations, larger matrices. So for a 2 by 2, I would expect you to be able to find an inverse by hand, be able to solve a 2 by 2 system of equations with matrices using inverses, the way we just did. For a 3 by 3 or bigger, you can use your calculator. So first thing we need to do with our calculator is make sure you have a matrix in there. So for my example, I have this as my matrix, as my 3 by 3 matrix A. So if you want to get a matrix into your calculator. And we can't use the one we did earlier when we were talking about determinants, the 1, 2, 3, 4, 5, 6, 7, 8, 9, because the determinant of that one was 0. You can't find an inverse. So once we have a matrix in there, to find an inverse, all we're doing is going and grabbing matrix A and using the x to the minus 1 button. And there's the inverse of matrix A, and I can convert this all to fractions. So I go to math, convert it to fractions. And there's the inverse of matrix A. I would hate to have to find that one by hand. That would be not fun. So that's to find an inverse. We just use the x to the minus 1 button with our matrix. If the matrix doesn't have an inverse, your calculator would come back with an error and say error singular matrix, and then it doesn't work. If you're trying to solve a system and you end up with a singular matrix, what that means is you're going to have to solve the system by hand, and that means you're either going to get a no solution or an infinite number of solutions for your system of matrices, for your system of equations. So that's what a singular matrix is going to tell you. If we want to solve a system of equations using this, so let's say, I'm going to go back to my matrices. So I have this for my matrix A, and let's say we have a system of equations, negative x plus 2y plus 3z, etc., etc. And that equals, I put in matrix B, I wanted to go to matrix B. There we go. I have a 3 by 1 matrix, so the solution is negative 3, 2, and 5. So those would be my constants. If I want to solve this system of equations, I'm going to do A inverse times B. Hit enter. There's my solution. I can convert that all to fractions. There would be my solution. X equals negative 9 halves, y equals negative 33 14ths, and z equals negative 13 14ths. That would be the solution to that system of equations. And if we got a singular matrix, the matrix didn't have an inverse, we would have to do row operations, solve it by hand, and we either get an infinite number of solutions or no solutions. All right, questions? Questions there? Okay. So our homework? So again, 2 by 2 you should be able to do by hand. 3 by 3 or above, you can use your calculator.